However, in the last class we have seen cosets of a subgroup of a group. So today we go through some examples. In last class we have discussed S3. S3 consists of permutations row 0, row 1, row 2, mu1, mu2, mu3. These are the nomenclature for S3, and you can also represent the same S3 as identity permutation, that is row 0 itself. Row 1 is a 3 cycle 1, 2, 3, and row 2 is the other 3 cycle 1, 3, 2, and mu1 is a 2 cycle which fixes 1. So this is 2, 3, this is mu1, and mu2 fixes 2. So this is a 2 cycle 1, 3, and last one is 1, 2, that fixes 3. So these are the elements of S3. The last class we have discussed the subgroup A3. Now we consider another subgroup of S3 consisting of row 0 and 1, 2 cycle. That 2 cycle I have chosen as 2, 3. When you consider this subgroup of S3, obviously this is a subgroup, and this is the subgroup generated by the element 2, 3. This is also the smallest subgroup containing 2, 3. So I have repeated these things because this is very important. So these are the subgroup generated by 2, 3, and that is the smallest subgroup containing 2, 3 of S3. And now you consider the cosets of this H1 in S3. So that is obtained by you can write different cosets using the elements of S3 itself. So once you consider this is the S3 and this is our H1 consists of row 0 and 2, 3. So there are so many other elements are there in S3. So if you choose an element, say 1, 3. 1, 3 is not in this subgroup. In fact, this is H1, and this is not an element of H1. So if you choose this 1, 3 to write the coset of H1, you can get 1, 3. We can operate 1, 3 to this H1. This is just a notation. So this the meaning of this notation is operate 1, 3 from the left to the elements of this H1. So this set consists of 1, 3 times row 0 and 1, 3 times 2, 3. Okay, so this is the set 1, 3 times H1. This is also called a coset of H1 corresponding to 1, 3. So or coset of H1 containing 1, 3. So this 1, 3 is always a member of this coset, because 1, 3 times row 0 is always 1, 3. And what is 1, 3 times 2, 3? How will you evaluate this? So we have to first of all we have to find the image of 1 here. Image of 1 is fixed in the second component, and that 1 is mapped to 3. So this is 1 goes to 3, and obviously the image of 3 is 2 here, and 2 is fixed. So this 3 is mapped to 2, and 2 is fixed. 2 goes to 3 and 3 goes to 1. So 2 is not fixed, 2 is mapped to 1. So this completes 1 3 cycle. Okay, so 1, 3, 2, 3 is nothing but 1, 3, 2. Therefore you can say that the coset containing 1, 3 of H1 is this one. Okay, similar fashion you can write the coset containing obviously coset containing 2, 3 is this H1 itself. So if we choose another element, coset containing 1, 2, coset containing 1, 2 is denoted by this one, and the first element obviously that is 1, 2, because 1, 2 times row 0, and the second element is 1, 2 times 2, 3. Okay, so this is nothing but 1, 2 times row 0 is 1, 2 itself, and when you operate this you can get what is the image of 1 here. 1 is mapped to 1 and that 1 is mapped to 2. So 1 is mapped to 2, and what is the image of 2? 2 goes to 3 and 3 is fixed in this component. So 2 goes to 3 and 3 goes to 2 goes to 1. So 3 is mapped to 1. So this completes one cycle. Okay. Okay, so this is the another coset of h1 corresponding to 1 2. Okay, so similarly, if you choose, obviously, if you can choose this 2 3 itself. When you take 2 3, what is 2 3 h1? 2 3 h1 is rho naught 2 3 times rho naught. So you please mind that this 2 3 is from the left hand side of rho naught. Okay, though this rho naught is actually the element, so both will give the same thing. But when you operate 2 3 to the other element, then 2 3 must be in the left of this element, because 2 3 2 3. Okay, so this is the coset corresponding to 2 3. So when you consider this 1 3 here, then 1 3 should be operated from the left hand side of each of these elements. Okay, so if you choose 1 2, then 1 2 should be operated from the left hand side. So if you choose 2 3, then 2 3 should be operated from the left hand side. Okay, in this case, this never changes, or this will not make any changes. Okay, so this is 2 3 itself. 2 3 times rho naught, and 2 3 2 3 will be identity, because 2 3 is a 2 cycle. Then the corresponding order of this 2 3 is 2. Then the corresponding element will be rho naught. So this is nothing but h1. So one thing we should observe is 2 3 h1 is equal to h1 itself. So that means if you choose an element 2 3 or permutation from h1 itself, then the coset containing 2 3 will be the same thing. Okay, so that will not change that set h1, okay, or that group h1. So these are the different cosets of h1 in S3. So similarly, you can take 1 2 3. This is another element in S3, and you can write 1 2 3 times h1. Okay, so this 1 2 3 times h1. What is 1 2 3 times h1? So first you operate 1 2 3 to identity. That means this element. So that will give 1 2 3 itself. Then the second element will be 1 2 3 times 2 3. So this will be the second element. So what is 1 2 3 times 2 3? So that is obtained by, the first thing is 1 2 3, and what is the second one? Second one, if you consider the image of 1 here, then 1 is fixed in the second component, then that one is mapped to 2. So this is 1 is mapped to 2. Okay. Now this, if you consider the image of 2, 2 is mapped to 3 and 3 is mapped to 1. So 2 is mapped to 1. So that will complete this 2 cycle. And if you observe the image of 3, 3 is mapped to 2 and 2 is mapped to 3. So 3 is fixed. So this is nothing but the coset of 1 2 3, coset of h1 corresponding to 1 2 3. Okay, so one thing you should remember is, if you consider 1 2 times h1, that is nothing but the set 1 2 1 2 3. Okay, so that is from this expression. Okay, from this expression you can get 1 2 3 times h1 is also the same. Okay, so this will be the same as 1 2 3 times h1. So which shows that whenever 1 2 times h1 equal to 1 2 3 times h1, okay, this need not imply that 1 2 equal to 1 2 3. We know that 1 2 and 1 2 3 are different permutations. Okay, so this never there is no implication for this coset equality. Whenever two cosets are equal, then the corresponding element need not be equal. Okay, so but if you consider all these cosets, then you can see that if you choose distinct cosets from this, okay, if you consider this one, then you will get 1 3 1 3 2. Okay, when you consider this one, then you can get another coset. Okay, 1 2 1 2 3. Similarly, if you consider this one, then you can get yet another coset corresponding to this coset of h1. Okay, but if you consider 1 2 3 h1, then you will get the same coset we have obtained earlier. Okay, similarly, if you consider 1 3 2 times h1, so you will get the same coset corresponding to this. Okay, so when you compute this coset, then the first element will be 1 3 2. Okay, the second element will be 1 3. So So please do it as an exercise. Compute this coset, then you will get this one. Okay, so this is same as this one. Okay, these two are the same coset. So these two are the if you consider these two cosets, then these are the same. Okay, similarly if you consider the cosets, these two cosets, then those are the same. And if you consider the coset corresponding to rho naught itself, what is rho naught times h1? So that will give rho naught and 2 3. So that will be the same. Okay, so this is same as the first one. Okay, our first one means the h1 itself. So that is nothing but then we can get these two are the same. Okay, that means whenever we consider these three distinct cosets, then we can say that these are the only possible distinct cosets of h1 in S3. Okay, so therefore we can collect all these three cosets, say these are the cosets. If we consider the cosets, first one is 1 3 times h1, and second one is 1 2 times h1, and the third one is h1 itself, that is nothing but 2 3 times h1 or rho naught times h1. Okay, so these are the distinct, okay, distinct and different cosets of this h1. Okay, if we consider these three cosets, we can say I'll call it as or we can write this what are the properties of this coset. Okay, the properties of these cosets are disjoint. If you consider any, I'll call it as some sigma 1 h1, sigma 2 h2, sorry, sigma to h1 again, and finally this is corresponds to rho naught h1. So I write the same symbol, rho naught h1. So if you consider these three cosets, you can say that this sigma 1 h1 union sigma 2 h1 union rho naught h1. So these are the distinct ones. So this gives the whole group S3 itself. So that will be a partition of the whole group. Similarly, each of this sigma 1 intersection, sigma 1 h1 intersection, sigma 2 h1 will be empty. Similarly, any pairwise cosets are disjoint. Okay, so this shows that this is because of the theorem what we have discussed yesterday. These cosets are nothing but the consequences of some equivalence relation. So cosets are in fact the equivalent class of those equivalence relations. So that will form a partition for the whole set, say S3. So that's why we are getting here this as the partition of S3. Okay, so this is one of the important examples discussed in the textbook, and similar examples are discussed with the group ZNs. Okay, Zn are the finite cyclic groups, and we have this Z and addition is a group again. So for the instance, we can consider the subgroup of Z as if you consider Z and addition. Okay, if you consider this group, then one of the subgroups of this group is nothing but 3Z. Okay, 3Z and addition is also a subgroup of this Z plus. Okay. So if you consider this subgroup 3Z, then if you choose 0, 0 is also an element of 3Z, then what is 0, the coset corresponding to, or coset containing 0 of 3Z. So that is obtained by operating 0 to the elements of this 3Z. Okay, in fact 3Z is nothing but multiples of 3. Okay, so 0, 3, 6, etc. This is minus 3, minus 6, minus 9, etc. And this is the subgroup 3Z of Z. And if you operate 0 to the left, to the every element of this 3Z from the left, then we denote that as 0 plus 3Z instead of 0 3Z, because this is again an integer. So to avoid the confusion, we won't write 0 3z, rather than this we write 0 plus 3z. So this will give 3z itself. Okay. Similarly, you can take another element from the z and write 1 plus 3z. Okay. What will give 1 plus 3z? 1 plus 3z is you need to operate 1 with add 1 to all these elements. So instead of 0 we will get 1, and here we have 4 and 7, etc. Here we have minus 3 plus 1, so that is minus 2, and minus 6 plus 1, that is minus 5, and so on. Okay, so this is 1 plus 3z. So this is another coset, and the next one is 2 plus 3z. What is 2 plus 3z? 2 plus 3z is corresponding to 0 we will get 2, and instead of 3 we have 5, that is 2 plus 3. So this is 2 plus 6, 8, etc. Here we have minus 1, minus 4, and so on. Okay, so this is the next coset. If you write 3 plus 3z again, you can consider any integer from z, and you can compute this. So you will get instead of 0 we have 0 plus 3, that is 3. Instead of 3 we have 6. Instead of 6 we have 9. Instead of minus 3 we have 0. Instead of minus 6 we have minus 3. Instead of minus 9 we have minus 6, etc. Okay, so this will give the same thing 3z. So which is equal to 0 plus 3z. So if you write the rest of the cosets, you can observe that those cosets are one of these cosets we have written here. Okay, so now you can say that there are only 3 distinct cosets. What is first one? 0 plus 3z. Next one is 1 plus 3z. Okay, and the next is 2 plus 3z. So these are the 3 distinct cosets of z. This is the cosets of 3z in z. Okay, so and we denote the set of all distinct cosets as z by 3z. In this case, this is the group and 3z is the subgroup. In general, if H is a subgroup of G, then we write G by H to denote set of all distinct cosets. Set of all distinct cosets. Distinct cosets. Okay, so this was the symbol. In the next class we will discuss the consequence of these cosets. We have already proved that these cosets comes from the these cosets come from the equivalence relation. So using the fact that the set of all distinct cosets from partition, we can deduce a theorem, a famous named theorem. So that is nothing but Lagrange's theorem. Okay, so that we will discuss in the next class. Thank you.